Okay. No, you do not need to write the formula. Okay, you do the calculation on paper and just write the answer. Only the answer box. All right, guys. Okay. Stop putting your chat messages now. We will have the discussions in the end of the lecture. Let me proceed with the topic for today, which is digital continuous wave modulation. Okay. Now, if you remember from your previous semesters, you have studied communication systems in which you have studied analog modulation, right? So analog modulation. So in analog modulation, you have studied AM, FM, and PM. AM for is the amplitude modulation, FM is frequency modulation, and PM is phase modulation. You have studied these things in your communication system course in level 7, I think, right? So now we are going to see the digital equivalence of this in this course, where we will have what is called as the digital modulation. Okay. Now, if you recall from your analog modulation, you have two signals that are used in the modulation process. So what are the two signals that we use? We use the message signal or information signal, and we use the carrier signal. So we have the message signal and the carrier signal, which is used in modulation. Now, in digital modulation, again, we still have the message signal and the carrier signal. So we have the message and the carrier, but the difference between them is that in analog modulation, the message is a continuous waveform. Message is a when we say continuous waveform, I mean to say continuous in amplitude. Okay, the amplitude is having a continuous range, continuous waveform in amplitude. Okay. In analog modulation, in digital modulation, the message is a pulse waveform. Message is a pulse waveform. Okay, so that means the message in analog modulation could be something like this, but the message in digital modulation is pulses, like you saw the NRZ pulses, right? So it will be discrete in amplitude. The amplitude levels are discrete. Okay, unlike the messages or the information signal in analog modulation, where the signal is continuous in amplitude, in digital modulation, the message signal is going to be like pulses, where the amplitudes are discrete. So if you notice here, the amplitude is having only two discrete values. Okay, if we can call this, say, plus A and minus A, masalan. Okay, so it has only two amplitude levels, either plus A or minus A. Okay, There is nothing, no other amplitude level in the signal. So digital modulation has a message signal which is digital, and analog modulation has a message signal which is analog. The carrier signal in both the cases is the same. So in the analog modulation, you had a high frequency sinusoidal carrier. In the digital modulation also, we have a high frequency sinusoidal carrier. So the carrier signal in both the cases remains unchanged. So for both of these, the carrier is high frequency, let me write it here, high frequency sinusoid. Okay, sinusoid means sine or cosine, or any shifted version of sine or cosine. Okay, so the carrier signal remains the same as in the analog modulation, and the message signal or the information signal is now a digital signal. Okay, so the ones and zeros which we map. So for example, if I can call this 1 0 1 0 0 1, right? So we have mapped those ones and zeros according to some line code. Okay, if you remember in the chapter 1, we talked about line codes to represent the digital information, the bits, as a waveform, and then that waveform will modulate a high frequency carrier signal. So our carrier signal will be like a sinusoidal signal of some high frequency. So we have a high frequency. Okay, so that's going to be our carrier signal. Okay, so that's the only difference between analog modulation and digital modulation. The carrier remains the same in both, but the message signal is different in digital modulation. Okay, so today we are going to discuss the digital equivalent of amplitude modulation. Okay, in analog modulation you have AM. We will see the digital equivalent of AM, and then we'll also see how to do digital modulation with emery transmission, right? So we can have binary transmission, and we can also have emery transmission, where we put multiple bits onto a symbol and represent them with multiple voltage levels. So we will see that that representation also in terms of the band pass signal, right? So we will look at the digital equivalent of amplitude modulation in today's lecture. Okay, if you want to take a screenshot of the screen, please take it now before I erase the whiteboard. I just leave it for 10 seconds, take a screenshot, and then I'll erase the whiteboard. Okay, let me erase the board now. So the digital equivalent of analog modulation digital equivalent of amplitude modulation which is AM is called amplitude shift keying. Shift, or we simply write that as ASK. Okay, so the ASK is the digital equivalent of amplitude modulation. And just to help you understand, I'm just going to make a message signal in amplitude modulation, which is a low frequency signal, time, and we'll call this as Vm of t, the message signal. And then we have a carrier signal, which is a high frequency. it's t, and if you call the carrier signal as Vc of t, and when you produce amplitude modulation, what do you get? What does the waveform look like? So you will have an envelope like this, and the carrier amplitude is changed according to the message signal's amplitude, right? That is the AM signal. So this is our amplitude modulated signal, VAM of t. But in the digital case, for amplitude shift keying, the message signal is going to be pulses. So there are only, if I take the binary case now, there are only two amplitude levels for a 1 and a 0, masalan, okay? So this is our Vm of t, but now we have only two amplitude levels, unlike in the analog case where we have a continuous variation of the amplitude level. Here we have only a positive amplitude level and a negative amplitude level. Or it can be a positive amplitude level and a zero amplitude level, right? So the digital modulation uses a digital or the waveform representation of a digital signal. The carrier remains same as in the analog case, so it's a high frequency sinusoidal waveform. Okay, so that's our carrier Vc of t, and because there are only two amplitude levels in the message signal, the amplitude modulated signal will have the carrier amplitude existing on only two levels. So for example, for a 1 and for a 0, we can have two amplitude levels, two different levels. So let's say this is the amplitude level for 1 and this is the amplitude level for 0. Again we have a 1, again there's a 1, and then there's a 0. So we have only two amplitude levels. That's one amplitude level, that's another amplitude level. So the information is contained in the amplitude of the carrier signal. So in the continuous modulation or the analog modulation, the amplitude of the carrier is changing continuously, and it is changing according to the message signal. In digital modulation, or the digital equivalent of amplitude modulation, the carrier amplitude is changing according to the message signal, but because the message signal now has only two possible amplitudes, either a plus A and a 0 or a plus A and a minus A, the modulated signal also has only two possible amplitude levels. That's for binary ASK, because binary means only two possible symbols, either a 0 or a 1. So for a binary 1, the carrier signal is represented with one voltage level, and for a binary 0, the carrier amplitude is represented with another voltage level. So there are two voltage levels for the modulated carrier, depending on whether the information being transmitted is a 1 or a 0. So therefore this will correspond to 1 and this corresponds to 0. So that's a 1, that's a 1, that's a 0. So that's our bit duration, right? That interval is our bit duration, okay, which we simply can call as TB, which is equal to 1 by RB, the bit rate, right? So the digital equivalent of amplitude modulation is amplitude shift keying, where we have the symbols represented by different amplitude levels of the carrier signal. So carrier is a high frequency sinusoidal signal, and its amplitude is changed according to the information signal. Now if you notice in the amplitude shift keying ASK modulated waveform, what you see is that the bit rate in one symbol duration, the in one interval of the symbol, how many bits are transmitted? Only one bit is transmitted. Yani it is one bit per symbol. During one symbol interval, only one information bit is transmitted. Therefore, the bit rate is equal to the symbol rate. So that is basically called as amplitude shift keying. Now, a simplification of this amplitude shift keying is done whereby rather than having a different amplitude level for the 0 bit, right? If you notice here, for a binary 1, we have one amplitude level. For a binary 0, we have a separate amplitude or different amplitude level for the carrier signal. But a variation of this can be done whereby for the binary 0, the amplitude level of the carrier signal can be made completely 0 itself. So that means during when the bit is 0, the amplitude of the carrier signal is made 0 volt. That means there is no carrier at all. So that variation of amplitude shift keying is called as on-off keying. So the reason it is done is because it simplifies the implementation of ASK. So it's called as on-off keying. So let me do it on the next page. And before I erase the board, I'll allow you some time to take a screenshot of this, of what's written on the board now. So you have like 5 seconds. Take a screenshot, please. Okay, let me erase the board now. And I will draw the so for the amplitude shift keying, for example, a binary 1 is having one amplitude level and a 0 is having a different amplitude level. And again, if you have another 1, it's a higher amplitude level. Again, a 1 and then a 0, masalan, okay? So it's 1, 0, 1, 1, 0, right? So that is amplitude shift keying, where a 1 is represented using amplitude V1 of the carrier, and 0 is represented using amplitude V2 of the carrier. Okay, so this amplitude here is V1 and this amplitude here is V2. Now a variation of amplitude shift keying is called as on off keying. In on off keying, the 1 is represented by an amplitude level, 1 represented using an amplitude level of the carrier, and a 0 is represented with 0 volt, 0 level of carrier. So if you draw the waveform for this, whenever there is a 1, the carrier has an amplitude level, and whenever it's a 0, the carrier amplitude level becomes 0. So there is no carrier there. Again, if it's 1, there is a carrier. Again, there's a 1, so we have the carrier, and for 0, it will simply be 0. So that's 1, 0, 1, 1, 0, right? So whenever there is a 0, the amplitude of the modulated carrier is made 0 volt. That means there is no carrier transmitted during the interval or 0. So that's why we call it as an on-off keying. That means if the information bit that we want to transmit is a 1, then the carrier is transmitted. It's like turning on the carrier. And if the bit we want to transmit is a 0, just switch off the carrier for that duration so that nothing is transmitted, and uh, that will be interpreted as a 0 bit. So we call this as an on-off keying, and the reason of doing this is because it simplifies the implementation of the amplitude shift modulator. So basically, to implement this, you'll just need to have an oscillator that produces the carrier signal, and the oscillator, for example, is connected to a switch. Okay, that's a switch. So that switch will be closed, right? If it's closed, the signal will go out. If it's open, nothing will go out on the other side. And the switch will be controlled by the bits, by the information bits. So if the information bit is a 1, the switch will close and the carrier will come out. If the information bit is a 0, the switch will open, that means nothing will come out. So whenever the information bit is a 1, this will be closed. And when the switch is closed, the signal from the oscillator, the carrier signal, will enter the output. But whenever it's a 0, the switch will open for that duration of the interval. That means nothing will come out. So the implementation of on-off simply requires a switch. The oscillator is needed anyway, whether you use ASK or on, but the implementation part requires a switch. So SWITC. Okay. So using the switch, you can produce on-off keying modulation. So if it's a binary 1 that is being emitted, turn on the switch, the oscillator's output, that is the carrier signal, will go out. And if it's a 0 being transmitted, turn off the switch, that means the carrier signal from the oscillator will not go out. It will just be turned off, so it will remain like 0, right? So that's a variation of amplitude keying, and it's called as on-off keying, or simply we write it as OOK. It's on-off keying. Okay. Okay. Right. So that's to do with the amplitude shift keying and on-off keying. That's the theory behind it. And again, what you notice is in one symbol duration, you're transmitting 1 bit only. So it's 1 bit per symbol. So it's binary amplitude modulation. It's binary amplitude shift keying. So when we write ASK or OOK, it implies that it is binary modulation. That means we are using only 2 symbols, either a 0 or a 1. We will now extend this idea to MRE modulation, and we'll call this as MRE ASK. Okay, MRE amplitude shift keying. I'll do that on the on a new on a fresh whiteboard. So please take a screenshot of the screen before I erase it. Okay, let's erase the board. So the next version that we are going to talk about is called as the MRE ASK. So MRE ASK is used when we have combined multiple bits, and rather than having the message signal consisting of only two amplitude levels, we now have m amplitude levels for the message signal. So for example, let's say I have a message signal with m equal to 4. So with 4 voltage levels, we can have, say, that's one voltage level, and let's say that's another voltage level, that's another voltage level, and another voltage level. So we are going to transmit 4 possible symbols, and each of them is represented by a particular voltage level. So that is our message signal Vm of t, and I'm using the example for m equal to 4 here. So we have 4 voltage levels, and if we call those voltage levels simply as, say, V1, V2, V3, and this is V4, right? So there are 4 voltage levels to represent the 4 symbols that we are going to transmit. And if we had such a signal modulating the carrier, that means the carrier signal, depending on which symbol is being transmitted, it will have 4 different amplitude levels. So after the carrier gets modulated, so I'm just going to draw it in sequence. Don't compare this with the message signal as it is. So that's 1 voltage level for one symbol, and then we can have a second voltage level for a second signal. So that's 1 voltage level, that's another voltage level, and then we can have a third amplitude level for the third signal. So that's another amplitude level, and then we can have the fourth one. You can have an amplitude level, or you can simply have an amplitude level of 0, right? So for MRE transmission, again, the information is contained in the amplitude of the carrier signal, and that is why we call it as the digital amplitude modulation or amplitude shift keying. So the information is contained in the amplitude of the carrier signal. So by observing the amplitude of the carrier signal, we can decide which symbol was transmitted. But now what you notice is in one symbol duration there are 2 bits. So that's 2 bits per symbol. Okay, and we are able to do that because we have now mapped 2 bits for each voltage level, and therefore we now require 4 voltage. So in general, for MRE ASK, what you will notice is for MRE ASK, you need 4 amplitude levels of the carrier signal after modulation. And generally what we do is one of the amplitude levels, we keep it as 0 volt, and the remaining m-1 amplitude levels will be used with non-zero voltage levels. Okay, so generally for the MRE ASK, we will have uh, for MRE ASK m-1 m-1 non-zero amplitude level and 1 amplitude level which is 0. Okay, so if you notice here in this example we have m equal to 4, and for this m equal to 4 we have one of the symbols represented by a 0 voltage level of the modulated carrier, and the remaining m-1, that is 4 minus 1, are represented by non-zero amplitude levels. Okay, these are amplitude levels which are non-zero. One of them is 0. So in general, for any value of m, we will have one amplitude level which is 0 and the remaining m minus 1 amplitude levels which are non-zero. Okay, this is called as Emery ASK, and like that we can do it for any value of m. We can do it for m equal to 8, m equal to 16, m equal to 32, 64, and so on. Okay, now if you notice here, we need 4 amplitude levels to implement a 4 array ASK, that is M array ASK with m equal to 4. So we are having amplitude level 0, which is the first amplitude level, and then we have this amplitude level, that's 2, that's another amplitude level, that's the third one, and the fourth one. So what is going to happen is if you keep on increasing m, then you need more and more amplitude levels to modulate the carrier, and that means the since the peak-to-peak range that can be supported by the electronic devices, or the maximum amplitude that the electronic devices can support, is limited, what will happen is the distance between the amplitude levels, or the separation between them, will become smaller and smaller as we increase the value of m. So if that separation becomes smaller, so the distance between one amplitude level and the other level, that's the distance between one level and the other level, right? And that's the distance between one level and the other level. So this distance, or the separation between the amplitude levels, will become too small, and when the channel affects the signal with noise, it will become difficult to distinguish which symbol has been transmitted, whether it is, say, if you use 0 0 for this, 0 1 1 0 1 1, and so on, right? So it will become difficult if you keep on increasing m, because the peak to peak range of the electronic circuitry is limited. You can't keep increasing the peak to peak range. All right, I've mentioned this before also. uh, Electronic devices, say, typically can handle up to about, say, 10 volt amplitude, or maximum some devices may support up to 15 volt. So within this peak amplitude level, you have to distribute all your modulated signals voltage levels. So that means if you keep on increasing the value of m, then the separation between those voltage levels is going to become smaller and smaller, and that means the noise will have a strong effect, and that can lead to errors in the received signal. Okay, so we are now going to see how we can overcome this problem, at least for m equal to 4. Okay, for the 4 m equal to 4 case, or for the 4 array ASK case, we can overcome this problem of having 4 amplitude levels. We are going to use only 2 amplitude levels, but with 2 amplitude levels we will create the effect of m equal to 4, right? That seems strange, but we will do that. There is a possibility of doing that. So we call that modulation as quadrature amplitude modulation. Or we write that as QAM. QAM is nothing but Emery ASK with m equal to 4. So here that means m is equal to 4. Okay, quadrature amplitude modulation. That means we are going to transmit 2 bits per symbol, or in other words, in one symbol interval, 2 information bits will be communicated. But instead of using 4 amplitude levels, we are going to use only 2 amplitude levels. How can we do that? The idea is very simple. We will use only 2 amplitude levels, but we will also use 2 carrier signals. Rather than using a single carrier signal, we will use 2 carrier signals. So 2 carrier signals of same frequency but oh, erase that, but shifted in phase by 90 degrees. Okay, shifted in phase by 90 degrees are used. So the idea of producing m equal to 4 is done now with two carrier signals. Rather than a single carrier signal, we now have two carrier signals. They have a phase shift between them of 90 degrees, and if and you all know that uh, the carrier signal is a sinusoidal signal. So if we want to choose two sinusoidal signals of the same frequency but 90 degrees phase shift, we can simply choose a sine wave and a cosine wave, because sine and cosine are 90 degrees apart in their phase. So we will have a carrier signal which is a cosine signal, and another carrier signal which will be of the same frequency, but instead of cosine we'll use a sine signal, and it can be a positive sign or a negative sign, right? Minus sign or plus sign. Either way, it is a 90 degrees phase shift with the cosine wave. So we are going to use two carriers. For each of these carriers, we will modulate them with only two voltage levels. So like we'll do a binary modulation of the carrier of the cosine carrier and the binary modulation of the sine carrier and add them together. So that means in the same interval, the added signal contains a cosine part and a sine part, and the cosine part can have either a 1 or a 0 representation. The sine part can have either a 1 or a 0 representation. That means in the same interval, we have now two bits of information, but using only two amplitude levels rather than four amplitude levels. Okay, so that's the whole idea behind quadrature amplitude modulation. So what we do now is, because we have two carriers, we have to divide our information stream. What's happened to my pen? Okay, right. Let me erase the board. Okay, let me erase the board and do it on a fresh whiteboard. So take a screenshot of this, and I will illustrate how this is working. Okay, here we go. I'm going to erase the board now. So what we do is basically we are going to have two carriers. So let's say that's an oscillator which is producing a carrier signal. I'll call that as cosine omega ct. Okay, I've kept the amplitude of the carrier simply as 1. The unmodulated carrier is simply 1, and that carrier is going to get modulated by some information bits. Okay, and then we'll produce a 90 degrees phase shift of this. So when we shift the carrier phase by 90 degrees, so if the carrier is a cosine, a 90 degrees phase shift of the cosine wave will produce, what will it produce? Minus sine omega ct. Okay, and that will modulate, or that will get modulated by another bit stream coming from our information sequence. So now what we have is, because we are having two carriers, we need to divide our information bits. We need to divide our information bits into two parallel streams. So we call this as the serial to parallel converter. So whatever is the information bit that is coming in the sequence, it is divided into two parallel streams. So the bits which are coming at say RB bits per second, that's our information bits, They are divided into two parallel streams, and the upper part of the information stream is going to modulate the cosine carrier, and the lower part of this modulator is going to modulate the carrier which is 90 degrees phase shifted. So the upper part we call it as say xi of t. So and the lower part we'll call it as xq of t. Okay, that's the name given to it. What does the I and q represent? I will tell you in just a moment. So the original information that is coming in, we'll simply call it as x of t. So the x of t information, the bit stream that is coming in, we will divide it into two parts. One is called as the xi of t, the other is called as the xq of t. And then xi of t modulates the cosine carrier, xq of t modulates the sine carrier. So because it is amplitude modulation, you can simply multiply them and get amplitude modulation. So what you have here is xi of t multiplied with cosine omega ct, and what you have at the bottom part after the modulation is xq of t sine omega ct with a minus in front because it's minus sine omega ct, right? And then we are going to add both of them together. So just add the two, and when you add the two, you get the modulated signal, which we'll call as say xm of t. Okay, xm of t, which is simply xi of t cosine omega ct minus xq of t sine omega, that's omega ct. Okay, so the modulated signal is xi of t cosine omega ct minus xq of t sine omega ct. Now what you notice is we are now dividing the information bits into two parallel streams, and one of the stream is modulating the cosine carrier and the other stream is modulating the sine carrier, and the cosine and sine are both uh, 90 degrees phase shifted with respect to each other. So because we have now two carriers, we can now represent the cosine carrier with only two amplitude levels and the sine carrier also with only two amplitude levels, and with these two we can have a combination of four symbols. For example, the cosine carrier can have an amplitude level corresponding to a binary 1, and the sine carrier also can be a binary 1. So 1, 1 or 1, 0 and so on. For example, let me just write here. Maybe I'll change the color. So the cosine could be representing a 1 and the sine could be representing also a 1. Or it can be 0 here and it can be 0 here, or it can be 0 here and a 1 here, or a 1 here and a 0 here, right? So now we have four combinations. So that's one combination that the two carrier waves can have, 1 1, or it can have another combination of 0 0. Both are 0 0, or one is 0, the other one is 1, or the first one is 1, the other one is 0. So now we have four combinations, and with four combinations we get the four uh, combinations of the symbols: 0 0, 0 1, 1 0, 1 1, right? So that makes it as m equal to 4. But if you look at each particular carrier, so if you look at the cosine carrier only or the sine carrier only, it requires only two amplitude levels because the values it can take is either 1 or 0. So for a 1 we can have one amplitude level, for a 0 we can have another amplitude level. So now we are able to achieve MRE ASK with m equal to 4 using just two amplitude levels for each of the carrier signals. Okay, so that's the whole idea behind quadrature amplitude modulation. We don't want to increase the number of amplitude levels, but we solve that problem of not increasing the number of amplitude levels by using extra carrier. Now, the, the beauty of this is that the carriers are 90 degrees phase shifted with respect to each other. So we call these 90 degrees phase shifted carriers as orthogonal carriers. Orthogonal carriers. And orthogonality means when two signals are orthogonal to each other, if you add them together, like we're adding here, so we are adding an xi of t cosine omega ct and xq of t sine omega ct here. When orthogonal signals are added together, it's easy to separate them out because they are 90 degrees apart in their phase, and that means so the separation becomes easier. Okay. Now, the upper part of this schematic, which is the xi of t cosine omega ct, is called as the in-phase component. And the lower part, which is the minus xq sine omega ct, is called as the quadrature phase component. Okay, so that's why we get the terms xi and xq. I stands for in phase and q stands for quadrature phase. Quadrature phase means orthogonal or 90 degrees shifted in phase. So you have an in phase component. That means this component is in phase with the original carrier, and the quadrature phase component is quadrature phase with the original carrier. So the original carrier is cosine, and this minus sine omega ct is 90 degrees phase shifted, so we call it as the quadrature phase component. Okay, so clearly you can see that we are now able to achieve m equal to 4 without increasing the amplitude levels. We have only two amplitude levels for both the carriers, an amplitude level corresponding to 1 and an amplitude level corresponding to 0. But now at any given time or during any given symbol interval, the two carriers may be having both ones, or one is 1 and the other one is 0, and vice versa, or both of them could be zeros, and that allows us, or that gives us four different combinations of the amplitude in the sum signal xm of t, the modulated signal, right? So by using this technique, we are able to produce Fourier ASK with only two amplitude levels. But obviously, the downside is that we have to use two carrier signals. Okay, and we call this as quadrature amplitude modulation, or QAM. Okay, I'll talk about the QAM in more detail. We'll discuss some more details about this in the next lecture, and we'll also talk about other forms of modulation going forward. And today I think we'll have to stop here. We're out of time, and I'll now allow you for the next 5 or 10 minutes to ask any questions that you might have. Okay, so you can ask me your questions, whatever doubts you might have, guys. If you want to speak, just turn on your microphone and ask the question. And
So
then
can you
once
hear
you
me?
finish asking the question, please switch off your microphone again. Otherwise, there's a lot of echo. Let's put a message about the short test. I have to know is the solved question will give us the marks after I finish the test. Yes, you will see the marks after you finish the test, but not after you finish the test. You will all the tests, you will see the marks after the end of day. Okay, if the test is today, after 12 o'clock in the night today, you can see the solutions. You can see the marks, and you can see your solution and what is the correct answer for each thing. Okay, you will not see immediately after you finish the test, but after 12 o'clock in the night. For every test after midnight, anytime you can see your outcome. What is your marks? What is your what is the answer that you entered, and what is the correct answer for that question? All of this you can see. You'll have to go back to the test and see it on the following day. That means if the test is today at 7 o'clock, you have to wait till midnight, till 12 o'clock in the night. After 12 o'clock in the night, you will be able to see everything. Okay, and the next question is when we say assuming that the signal is free of ISI, what does it mean? ISI means inter-symbol interference. Okay, now what happens is if you, okay, let me illustrate that. Right, I'm going to erase the board, guys, just to answer one of the students' question. Quickly take a screenshot.
Doctor, can you hear me?
Okay, let me erase this now. What do we mean by zero ISI? Zero ISI. ISI means inter-symbol interference, right? That's the ISI is the acronym for inter-symbol interference. And when we say zero ISI, it comes from pulse shaping. Okay, you are not studying pulse shaping in this course. Pulse shaping. That's basically we never transmit a rectangular pulse. Okay, we never use rectangular signals because rectangular pulses require infinite bandwidth. I mentioned this some point before the university closed. At some point, I said I remember doing this. Okay, where we said that we never transmit rectangular pulse because the rectangular pulse has a spectrum which is a sync signal. That means it has infinite bandwidth. So we can't transmit a signal which has infinite bandwidth. So what we do is we shape the pulse and say make it like the frequency domain representation, we make it in the time domain. For example, we have a sync pulse. Okay, rather than having a sync spectrum, we make the time domain pulse as a sync pulse. And then when we transmit each bit, we transmit the bit using this pulse, or we represent the bit using this pulse, for example. And let's say we have another bit, the next bit, and the next bit will be done in such a way that when the previous bit is going through its zero, the next bit is going through its peak. So if you see now, so that's one symbol. The red one is one symbol, and the blue one is another symbol.
Hey, Doctor.
So the red is one symbol, the blue is representing another symbol. And the way they are arranged is that when the red is going through zero, the blue is going through its peak. So, and when the blue is going through the zero, the red is at its peak. So this means that if we sample at the correct moment, if I sample exactly here, I will get the maximum value for only the red symbol. The blue is zero, and therefore there will not be any interference between them. But if that sampling is slightly offset, if there is no proper synchronization, and if we end up sampling, say here, the red has a decreased amplitude and the blue is having an increased amplitude, that means the blue will now interfere with the red. Okay, so that causes inter-symbol interference, and inter-symbol interference also happens because of what we call as the variation in the delay. Okay, if all the symbols arrive after the same delay, there won't be any problem. But if each of them is undergoing a different amount of delay, then they will be staggered, and that will cause problems and create inter-symbol interference. Okay, so that is what we mean by zero ISI. When we say zero ISI, that means they are perfectly aligned and we are sampling at exactly the correct time. So that means one symbol and the neighboring symbol is not interfering with each other. They are not affecting one another. So that is what we mean by zero ISI. What do we good? Okay, distortionless, of course, yes. When we say zero ISI, that means the symbols are not distorting each other. Okay, there may be other forms of distortion by noise or other factors, but the symbols are not affecting each other. For that, we need to implement our receiver correctly. The sampling has to be exact, it has to be synchronized and perfectly aligned. It's ideal, but we do design systems which synchronize. That's why we have other mechanisms which avoid or minimize this intersimple interference. We need to minimize this. Obviously, it will not be zero, but it will be as minimum as possible. Okay, just like we can't have zero error probability, but we do techniques which minimizes this to be so small that we don't face any problems. Okay. To make it exactly zero, that means our synchronization should be exactly perfect. Obviously, we can't do 100% perfect synchronization. So what we do is we achieve as little ISI as possible. Abdullah Muhammad Murray, don't write the fraction. Okay, for example, if you have an answer, say 0.5, you have to write it as 0.5. Don't write it as 1 by 2. Guys, for today's test, if your answer is 0.5, you'll have to write it as 0.5. If you write it as 1 by 2, it will give you an error. Okay, so if you have fractional answers or decimal, you'll have to use the decimal format, not the fraction format. 1 by 2 equals 0.5. You will have to write it as 0.5, not 1 by 2 in today's short test, guys. Okay, please follow the instructions, and there are multiple choice questions, which is okay, you're familiar with. And for the calculated answers, you don't need to write the formula, you don't need to write anything. Simply write the answer as a number. Okay, if it is 1.47, just 1.47. Okay, what do you mean explain more? Just write the answer as a number. Okay, if the answer is 0.5, you have to write it as 0.5. 0.5 savi 1 by 2, right? But you should not write 1 by 2 as the answer. You have to write it as 0.5. All right, guys, any other questions related to the topic? Yes, I think there is some announcement from the Education Ministry. I think there is some majlis, or what do you call it, a meeting of the college today, and we will have some information today. I think you are going to have a final exam for 20 marks. Okay, so so that means whatever you have done till now, I will be scaling it to 80%. That means the short test 2, which I talked about, maybe I will make it for 20 marks and use it as the final exam. Okay, well, that's an announcement that came recently from the ministry, and we are obliged to follow the instructions of the ministry, so we will follow the instructions of the ministry. Okay, so that's how it's going to be. So there will be a final exam, which is most likely going to be an online exam, but it will be for 20 marks. Okay, this short test will count in the 80%. What you're doing today, it will count in the 80%. What I said I will do again next week, I will include that as your final exam. Okay, but it will not be next week. I think for the final exam, the timetable will be announced by the university, and according to the timetable, you will have to do your exam. Like the normal final exams, how the jadwal is announced, you will get a timetable for the exam date and time, and you have to take us on that date and on that time. Okay, inshallah, may Allah help us all, may Allah help you. Inshallah, you'll be fine, don't worry. Okay, just study well. If you do your work, you will be fine. Okay, just prepare, study. You have the material with you, you have the textbook, so just read and be clear about the topics. Inshallah, you will be fine. Regarding the previous quiz, okay, I think you should be able to see your darajat for the previous quiz also. So please have a look. You have the quiz marks. It is visible now, I think. So regarding all your quizzes and the short test, okay, you will see the solutions and everything after midnight on the day of the test. Okay. Right, guys. Okay. If you have any other questions, ask me very quickly. We have another 2 minutes maybe, and then I'll have to move on. Where can you see it? What do you mean? In the grade center, you can see in the grade center. If you go to your grade center, and I think within my grades, you should be able to see all your grades for all the previous quizzes. Where you see for all your previous quizzes, right? The answers, I think you'll have to go on that quiz. Go back to that quiz and click on it, and you should be able to see. It will give you what answer you entered and what is the correct answer. Both options you will be able to see it. All right, guys. Okay, if there are no other questions, I'll have to take leave of you. We'll meet again in the next lecture next week. Till then, take care, stay healthy, stay at home, and do your work. Okay? Assalamu alaikum. Quiz 4, you can't see it. I don't know why you don't see quiz 4. It should be visible, man. Check in your migrants. Let me quickly see. It's not visible. Okay, let me check it. Okay, you should be able to see that. The answers for each quiz. The answers for each quiz are visible, man. I don't know how. I don't know how it appears for you. I'm not sure. I have made the settings for it to be shown after the midnight of the day of the quiz. Okay. I think you'll need to navigate on Blackboard and find a mechanism for that. I'm not sure how it appears for you, as a student. Check it, please, okay? If I find it, I will let you know. All right, guys, okay, I'll need to take leave now. I have to go for another session. Take care. Assalamu alaikum. Inshallah, we'll meet again in the next lecture.